Welcome to this session on ISO 26262 with Model-Based Design, a hands-on Simulink tutorial with an X-by-wire example. In ISO 26262, most artifacts, such as the item definition, HERA, safety concepts, and software requirements, are traditionally written in natural language, which is flexible but often ambiguous and prone to inconsistent interpretation across teams. Executable specifications address this challenge by expressing requirements in a precise, machine-interpretable form that can be validated directly through simulation and analysis. A requirements table in Simulink provides a formal, structured, and unambiguous way to define system and software requirements, moving beyond the limitations of natural language descriptions. Because the table is executable, engineers can simulate it directly to validate that the specified behaviors align with the intended system functionality, enabling early detection of requirement defects before implementation. Its formal semantics also allow the use of formal methods and verification tools such as Simulink Design Verifier to automatically analyze requirements for logical consistency, completeness, reachability, and potential conflicts. This makes the requirements table a powerful mechanism for creating high-quality, verifiable specifications that integrate seamlessly into model-based design workflows, particularly in safety-critical domains like ISO 26262. We will use a headlight controller as an example to demonstrate how a requirements table can be used to formalize behavior, eliminate ambiguity, and enable simulation-based and formal verification of requirements. Here shows the simulation in Simulink. The headlight can be controlled manually by the driver through the headlight knob, allowing direct selection of the desired lighting state. Alternatively, the system can operate in an automatic mode, where the headlight behavior is determined by multiple factors, including the ambient light level measured by the light sensor, the validity of the sensor signal, and the vehicle's ignition status. Alright, here are the textual requirements for the headlight controller. Please take a moment to review them carefully. Can you identify any potential issues or ambiguities? As you might expect, several issues become apparent. The first is inconsistency. Some of the highlighted requirements contradict each other, leading to conflicting interpretations of the intended behavior. The second issue is a different kind of inconsistency. The requirements fail to specify which requirement takes precedence when multiple conflicting rules apply. Without explicit priority or arbitration rules, for example, whether manual driver input overrides automatic control, or how to resolve sensor faults versus ignition state, teams will make different implementation choices, increasing the risk of inconsistent behavior across components. The third issue is incompleteness. The requirements do not specify what the controller should do when the ambient light level falls between 100 and 200 lux. This undefined region leaves the system behavior unclear and can lead to gaps in implementation or inconsistent assumptions across teams. The fourth issue is ambiguity. The highlighted requirement lacks sufficient detail to guide implementation, leaving it open to multiple interpretations. Without clear guidance on the expected behavior or conditions, developers may implement it differently, potentially leading to inconsistent or incorrect system behavior. Here's the implementation in Simulink that utilizes the requirements table to capture and verify formal executable requirements. The requirements table organizes requirements into a structured tabular format where each requirement is defined by two key elements. The precondition, which is a Boolean expression specifying the conditions that must be true for the requirement to be evaluated. The action, which defines the system's output or change in state when the precondition is met. It's the executable code that is run if the precondition is satisfied, thereby making the requirements executable for simulation and verification. Using the requirements table in conjunction with Simulink Design Verifier enables formal verification to identify issues like inconsistency and incompleteness. For example, Inconsistency may be found where requirement 1 conflicts with requirement 6, while incompleteness is illustrated by the lack of defined behavior for sensor levels between 100 and 200 lux, a gap not covered by requirements 4 and 5. Additionally, the requirements table provides executable logic, allowing us to simulate the system. If the model contains the previously discussed issues, such as conflicting or incomplete requirements, Simulink will flag them by generating errors and warnings during the simulation. This demonstration shows how to use the requirements table block for formal verification and simulation. To analyze the requirements for consistency and completeness, navigate to the Table tab and click Analyze Table. This action triggers Simulink Design Verifier to perform a formal analysis. The resulting inconsistency and incompleteness issues will be highlighted directly in the table for immediate review. Additionally, we can perform simulations using the requirements as executable logic. If the requirements table contains the flagged issues, Simulink will automatically issue corresponding errors and warnings during the simulation run, pinpointing runtime conflicts or ambiguous behavior. After reviewing the identified issues from both the Simulink Design Verifier analysis and the simulation results, we can now fix and refine the textual requirements in the table as demonstrated. Please take a moment to pause and review the corrected requirements. After the fixes, here is the clear and resolved version of the requirements table. Here is the refined requirements table. Please note two key changes. The symbols in the index column confirm that the requirements are prioritized sequentially by their index order. We have also introduced a duration column to implement hysteresis, which is necessary to prevent undesirable flickering behavior. Here is the final demonstration, showing the analysis and simulation performed on the refined requirements table in Simulink. Since we addressed the prior issues, the analysis should now pass, and the simulation should execute without errors or warnings. The requirements table in Simulink is a powerful block best suited for modeling discrete condition-action-based logic that can be directly executed and verified. It excels at capturing logical requirements which define operational rules and is very effective for safety requirements that involve fault handling or critical state transitions. It can also manage basic timing requirements, such as hysteresis, using its duration feature. However, it is a poor fit for requirements that describe structure or continuous non-functional constraints, such as interface, performance, or architectural requirements, which are better addressed through documentation, other dedicated Simulink blocks, or external verification methods. Executable specifications are foundational to the shift-left approach in model-based design, dramatically accelerating the development and iteration of safety concepts. By establishing digital representations of the system, engineers can move validation to the beginning of the life cycle, enabling rapid prototyping, analysis, and verification of safety requirements in a virtual environment before any physical implementation. This early detection of design flaws and comprehensive exploration of fault scenarios allows for iterative refinement of safety mechanisms at a fraction of the time and cost associated with hardware-based testing. Ultimately, model-based design provides a more agile and robust process for achieving, documenting, and demonstrating system safety, thereby supporting compliance and eliminating costly late-stage surprises. We have now completed our coverage of the requirements table and its role in executable specifications. In the next session, we'll explore Part 6, Product Development at the Software Level. I look forward to your participation.